Good morning, everyone, and welcome to the last day of our summer school. It's my great pleasure to introduce Vivian Chen, who will be giving us a lecture on dialogue systems. Vivian has come a long way from the National Technical University of Taiwan to be here with us today. But she's used to traveling a lot. She's done her PhD at the Carnegie Mellon in Pittsburgh. So we're looking forward to her talk. Thank you all.
Hello, everyone. I'm Vivian Chen from National Taiwan University, and as mentioned, I graduated from Carnegie Mellon. And during my PhD, I worked on dialogue system, but at that time, nobody working on that area. So I want to cover the dialogue system as the last application about natural language processing. So I want to start with a famous movie, which is Airman. And from this movie, you can see that Airman has a very good intelligent system called Jarvis. Jarvis can help Airman to open light or close the light, and also download some document for Airman, and also fix some component for Airman. Based on this movie, we can imagine in our future, everyone can have their own intelligent system, and this intelligent system is supposed to help the user to finish a lot of tasks. That's why we want to have our intelligent system, just like Apple Siri and Google Assistant, and also Microsoft Cortana. And these days, smart speakers are very popular. For example, Amazon's Echo and Google Home, and also Apple also have their smart speaker called HomePod. And very recently, Facebook provide a product which is called Facebook Portal, which is enable the user to do the video Skyping using this device. But in the back end of this device, they borrow the technology from Alexa. But Facebook want to collect more data so that they can also build their own intelligent system. And from this example, you can see that a lot of companies trying to deliver their own intelligent system to users, no matter about virtual assistant or the physical system. But the first question comes to us, why we want to use natural language to do the interaction? Because previously, a lot of people are used to using the click and do the interaction with the GUI. But these days, why we want to change the behavior to the natural language? Let's see the last year's statistics. Currently, the total population is around 7.6 billion, and there are 4 billion users are internet users. We also see that there are 3 billion active social media users. So if you use Facebook every day, then you are one of this group. But these two numbers are amazing. There are 5 billion unique mobile users. This number is more than the number of internet users, as you can see that. And also about 3 billion users are active mobile social users, which means this user are used the mobile device to do the interaction, for example, the communication like WeChat or WhatsApp or Facebook Messenger. So based on this behavior, we will see that a lot of people move their interaction behavior from the laptop and desktop to mobile device. So if you have a mobile phone or smartwatch, then the screen is slightly small. It's not very convenient to directly use the interaction by click or typing. So the more nature and convenient input of this device evolves towards speech. And that's why in our movie, we also imagine our future life, we can only speak, then the machine can understand us and trying to help us to finish a lot of tasks. So let's look at our daily conversation. First of all, some conversation belong to chit-chat. We only want to kill some time using chatting. So this is the first category. And the second type is you have an answer and you want to get you have a question and you want to get an answer to this question. For example, what is today's agenda? What does NLP stands for? In these two questions, we want to get some correct information, so we call this behavior as information consumption. And the third one is more complex. It also includes information consumption, and we call this type as task completion. So in this interaction, the user wants to finish certain tasks, for example, purchase a ticket or booking a table or schedule a meeting. So by these three examples, you will see that sometimes you want to get some information about this. For example, want to get the availability of the ticket, and then you will try to decide which ticket you want and to finish this transaction. So the task completion is more complex. And the last one we call decision support. In this category, sometimes you will have a question. Is this summer school good to attend? For this question, there's no correct answer, although we think the answer is yes. But this is not, this question do not have the correct answer by their own. This question you only want to ask because you want to collect some feedback so that you can make your own decision, so which is different from the information consumption mentioned before. So based on these four different types of conversation, we can categorize it into two parts. The first part is about social chit-chat. Social chit-chat means that you do not have a certain goal, then you just want to kill the time. And the other three types of conversation belong to task-oriented dialogue, which means the user has a certain task or the goal in their mind, and they want to satisfy this goal. For example, they want to get an answer for a certain question, or trying to complete some task, or trying to collect the feedback so that they can help them to make their own decisions. So that we can see this is the example about request for this intelligent system. So in this example, you can see that almost all requests belong to task-oriented. For example, show me next week's schedule, or get today's agenda, when some person's anniversary, and so on. And there are a lot of popular requests behind the intelligent system belong to task-oriented. But one exception is about tell me a joke. A lot of people want to talk to the intelligent system and ask for the joke, but which belongs to the chit-chat part. So if you want to imagine how can we build an intelligent system for our mobile device, it's pretty easy. We just think about we can change our app behavior into bot. A bot just like an app, which is responsible for a single domain. For example, this is the interface for a beauty salon app. And in this interface, you will see there are several menus, and you will just click appointment to make the appointment and trying to fill in for the form so that you can make the reservation. So this is the traditional app format. The user needs to follow the design developed by the developer, then have the tree structure to click so that you can enter the certain area to make the reservation. But if you change the behavior into bot, just like this, the user can directly initiate this dialogue. For example, haircut on Saturday. The machine trying to understand the semantic behind this sentence and help to find the availability of the time so that the user can choose the time slot and then finish the reservation. So these interactions are quite different from the app behavior. The main difference is that these users can initiate this dialogue instead of following the GUI design, so which is more user-centralized behavior. So in the conversational AI, there are two different branches developed in a different way. The one belongs to chit-chat, another one belongs to task-oriented. The reason of developing these two areas separately is chit-chat part, we want to have our conversation more engaging so that the conversation should be slightly longer because we don't want to have a very short conversation, which may mean not very engaging. But another one, task-oriented, you don't want your drivers to talk to you too much. They just finish their task, so you want the conversation as short as possible. So these two branches have so different objectives. So in the machine learning area, we want to have the objective function for this machine. So chit-chat part, they want to have a longer conversation. However, the task-oriented system want to have the shorter conversation. The objective functions are opposite. That's why these two areas are developed separately. But these days, they're trying to merge together. The reason is, as a human, you can easily switch between these two types. Some interaction belong to the chit-chat, and sometimes you can quickly switch to the task-oriented mode. But there's also a lot of issue between this, about this convergence. So we will talk about the difficulty and why they want to merge together and why they separate develop in the current research area. So let's start with the task-oriented dialog first. On the left-hand side, you will see the drivers, and on the right-hand side is Baymax. Baymax actually, it is a physical robot. However, they also need to have the good dialogue system so that they can understand the user. The Baymax focuses on the healthcare domain. They can understand what the user said and trying to provide the healthcare-related suggestion for the user. So in a task-oriented dialogue system, usually you will see this framework for almost every system. First of all, the user will say something by their speech, and you need to have a speech recognition system to recognize the speech signal into text. So this user said, are there any action movies to see this weekend? Definitely, the user can directly type this information to the chatbot. So after we get the sentence of this input, the first part of the dialogue system is trying to understand the language. That's why we are here. We want to know how to do the natural language processing. We want to extract the semantic behind this sentence. For example, based on this sentence, the user wants to search some movies. So the user's intent may be movie request. However, not every movie are satisfy this constraint because they have the constraint about genre and also date. The genre should be action movie and date should be this weekend. So we want to extract this semantic corresponding to this input sentence so that we can understand what the user wants. Until now, probably you can imagine we can easily construct this semantic frame into a query, and we can search a database. Then we can return the movies which satisfy this constraint. Yes, however, it's not very easy. The reason is if you do the interaction for example, customer center, another component is very important and essential, which we call the dialogue manager. In this component, after they interact with the database, sometimes you may get maybe hundreds of movies satisfying this constraint. But it's impossible to directly return the whole list of the movie to the user because it is not information retrieval system. The user do not have enough time to look at the whole movies. What you want to do is you need to help the user to narrow down the search space so that they can finish the transaction or finish purchasing the ticket. So how about you just ask additional constraint? For example, you can ask, do you have the location constraint so that you can narrow down the search space so that only several movies can be recommended in this procedure? And sometimes you don't need to add the additional constraint because it depends on your return list. If your return list only contains like 3 movies, then in this situation, you can directly return these 3 movies to the user. So this dialogue management, just like the brand of the agent, they need to decide based on current scenario, what kind of action is the best action to interact with the user. So this is very difficult, especially in the current technology. We do not have a very good approach to fulfill the user's goal because we don't know which system action is the best action to interact with the user. After we design the system action, we can generate the corresponding language and get back to the user. So in the next turn, the user can say the second sentence, and the language understanding component will try to extract the semantic again and merge with the previous semantics. Then Dialog Manager will design the next system action. And iteratively, we will do this dialog system as this framework. So let's start with the first component, which is language understanding component. Usually, language understanding contains 3 parts. The first one is domain. We need to define the domain first, and then decide the intent of the users. The third one, we need to fill the slot. What do they mean? First of all, we need to design a domain. The domain, for example, this sentence is, find a good eating place for Taiwanese food. And in your backend, usually you have multiple knowledge database, restaurant database, taxi database, and a movie database. And domain, you need to design a domain which belongs to which database you need to search for in order to get the corresponding information to this user. Okay, so which is pretty easy because you just need to collect the data for the sentence and also the corresponding domain. Then you can train a classifier to do the sentence level classification to map the sentence into a certain domain, which is the first task, domain identification. Okay? After you design the domain, you need to figure out the user's intent. Based on this sentence, this database has several queries. For example, you can find restaurant based on this database. You can find the price of the restaurant or find the type of a restaurant. You can have different type of query. Which query is associated with this utterance? Because the user wants to find good eating place, so it belongs to find restaurant. So it's also very easy. You can collect the data, including sentence and corresponding user's intent, so that you can also train a classifier to do the sentence level classification and map the utterance into the user's intent. But the third one is more complex. Third one, we call it slot filling. This is the database we have, and this is the user's intent we want to query. But we need to extract the constraint about the restaurant. So here is an example of this restaurant table. There are a lot of restaurant and corresponding attributes, including rating and type. So the goal for slot filling is we need to extract good is the value of rating slot, and Taiwanese is the value of type slot. So why we call it slot filling? Because we have several slots. We need to fill in the value based on the sentence, just like extract the constraint about the restaurant. The reason is we want to extract this semantic frame. If we have the rating is equal to good and type is equal to Taiwanese, then we can easily construct a query to search the database and then get the return list about the restaurant which satisfies this constraint. But this is not the same as the previous sentence level classification problem. In this task, we need to do some sequence labeling. For example, we can assign a annotation label for each word. O indicate out of concept, and B rating indicate beginning of rating slot. So we will know that good belongs to the rating slot. And there's also the I rating, which means if you have a sentence which is very good eating place, so very good should be the phrase belong to rating slot. So very will be labeled with beginning of rating, and good will be labeled with internal of rating. Then we will know these two words need to merge together, belong to the same slot. There are several examples. For example, New York should belong to the same slot. So how to process the slot filling? You will already know there are a lot of models like Airman model. You can use the simple LSTM to do this sentence level tagging. Given each word, you will assign each tag for each word by LSTM. And you can also allow the model to consider the context of the input. Then they may have a better understanding. Definitely, because we usually have the whole sentence, and we will design the whole sentence for the extract the constraint. So you can use the bidirectional LSTM. You can do the forward and backward, and to tag each word afterwards. They will have a better result. The reason is sometimes if your sentence is from Taipei to Athens, so Taipei, if you look at the word following the Taipei is to, then you will better to design Taipei is the origin city. So you can also think about a lot of different variations. For example, you can use encoder-decoder architecture, just like machine translation. You will encode the whole sentence and then decide to do the tagging afterwards. Then you can add an attention mechanism to allow the model to focus on a specific input. However, although we have 3 different tasks, we do the domain identification first, and then do the intent. The following part is doing the tagging. The previous approach, like traditional approach, we will use different methods. But recently, all tasks, we use the neural network to do the 3 tasks. So we can consider to merge the 3 tasks together. We can do the joint semantic frame parsing. You can easily think about, we have a single LSTM, the sequence-based model, and in the beginning, we tag each word one by one using slot filling. And in the end of sentence, we will tag the intent as our intent output. So when we train this model, the intent information and the slot information will influence to each other. So we may have better performance, and we can only have one single model to perform the whole task. And why interaction between these 2 parts are beneficial? The reason is, for example, if your intent is find a song, and it's more possible to have a slot, which is maybe the singer slot, which is less possible to have the slot, which is the director slot. So you will see the slot and intent may have some correlation. So if you model in a joint way, you will get the benefit for this type of joint approach. And another architecture is called parallel. You can do the encoder in the beginning and to have two branches. One branch decide the intent, and another branch trying to start tagging. And in this architecture, the information can also share to each other for the encoder side. So no matter sequence-based model or parallel-based model, they're trying to model the intent-slot relationship. However, they're trying to model this relationship in an implicit way, which means they just want this model to learn some shared parameter for these two parts, but they do not explicitly model whether these two information are, what's the correlation between this intent and slot. So another model, which is called slot-gated joint understanding. It includes the left part is about slot filling, and the right part is the intent prediction. And they use the attention mechanism for both parts. And if we want to use the joint model, we can merge these two parts together. And here, you will have the information about the intent. So here is the intent prediction result. And they embed another slot gate, which is we want to model the relationship between the intent and slot. So this intent will provide us the informative cues so that we can have the better prediction about the slot. The takeaway message is this value G will be larger if the intent and slot are strongly correlated. For example, if you want to find a movie, it's more likely to have a slot, which is actor slot or director slot, and it's less likely to have a slot, which is like singer, because singer is less likely associated with the movie area. So you will see this gate will provide you the information about their relationship and get a better result. However, this language understanding area is not very simple because in previous framework, we consider each sentence independently. So we only extract the semantic by the single sentence. However, during the conversation, a lot of information should be aggregated. And if you only consider single sentence, sometimes it's very difficult to extract the correct semantics. Let's see example. If you want to book a restaurant, and the user said cash code for 6. So 6, do you think it belongs to the number of people or the time slot? Actually, this is very ambiguous because based on this sentence, it can be number of people or the time. But if you look at the previous context, book a table for 10 people tonight. So based on the previous sentence, you will know that the number of people is equal to 10. So 6 should be the time slot. So if you only consider the current sentence, you may not be able to extract the correct slot for this sentence because you do not consider previous context. But sometimes you will have a lot of context in your conversation, and which context is relevant to design the current semantics. It's very difficult to design. For example, if you want to extract the semantic for the current sentence, let's do 540. And there are so many related information in the previous history. So we can consider to model each previous history as a vector and put into the memory. And when we decide to understand the current semantics, we will extract the related information from the memory and use that embedding to help us to understand the current semantics. Let's do 540. based on this conversation, you will understand that, oh, because the system provided several time slots, so they select one from the time slot. So 5:40 means 5:40 p.m. and corresponding to the movie ticket here. Okay. So how to do this approach? So this is the previous utterance, and you have the current utterance. In the classical way, you would directly use the Airman tagger to tag the current sentence. But we want to include the previous context, so we just try to encode each sentence in the history as a vector memory. And we would design an attention mechanism to extract the corresponding history and fill in the corresponding history to the current model. So the whole model will be trained in an end-to-end manner, and it will automatically decide what kind of information needs to be extracted in order to understand the current sentence correctly. So here the idea is trying to incorporate the contextual information during the tagging. So it's like trying to track the dialogue state, and we'll describe what dialogue state is. As the same example, this model will automatically decide these three sentences are highly related to the current sentence. And the highest attention weight is the first sentence. Usually the first sentence is very important because the user will say the main goal for the whole conversation. They want to purchase a ticket, and this ticket is about this movie. Okay. And the second highest one is this one. So this is correct because the system provide this user several time slots. So they select one from this list. But they also pay attention to this sentence. So this sentence is irrelevant, but they also automatically decide a slightly higher weight. The reason is this sentence is asking some number, how many tickets. So if you only look at this sentence, let's do 540. It's also possible to have like 540 tickets, but it's based on our common sense, it's not very likely. But they also pay attention to this sentence because they think it's relevant to the current understanding. But in this example, finally the model can automatically extract the semantic in a correct way. They will decide, oh, this is the time slot. Based on this whole, the merged information from the context. And you may know that there are so many recent advances in natural language processing based on the contextual embedding, like Airman or BERT. So this contextual embedding already show that it boosts a lot of understanding performance. Just use this pre-trained language model. So how about we use this type of approach and directly to understand our current sentence? It's possible, however, there's some issues. If you directly use the current pre-trained language model to your understanding part in the dialogue system, you just like to treat the current system only allow the text input, because which is the natural language input. But in the conversational system, usually the input will come from speech. So you will have the first pass by the acute ASR, which is speech recognition. If you look at this sentence, live all life to Morocco. If you only look at this sentence and put it into the language understanding component, it's very difficult to extract the correct semantics. The reason is they include a lot of speech errors. The actual speech should be lived or fly tomorrow. So if you directly use the input as the natural language and use the natural language processing trying to extract the semantic, you may have some issues. So we need to consider the speech recognition error. That's why we cannot directly use the pre-trained language model to our task, because there is mismatch between written and spoken language. If you use the pre-trained contextual embedding, which is trained from the written text, so they do not include any recognition error. So if you apply to the spoken language, including some errors, there's a mismatch. So we want to consider, is it possible to build the ASR robust contextual embedding? ASR is automatic speech recognition. Our embedding will be slightly better for the spoken area. Trying to learn our embedding specific for spoken, and which may have better performance if you apply to the spoken language input. One possibility is we can use like transformer to adapt this transformer and to allow them to fit the ASR lattice. What is ASR lattice? ASR lattice is provided by the speech recognition. They may include a lot of information, and this lattice may include the correct word. For example, this is the transformer. The transformer is the backend model behind the BERT or like the GPT. So this is the lattice. After you do the ASR, which is the speech recognition, you may have multiple paths, and you will have the probability between each path, and you want to include the whole path and fit it into your transformer model. But your transformer model only trained on the written text, which is the flat architecture, flat structure. If we want to allow this model to fit the ASR lattice, we need to do some adaptation. In this paper, which is very simple, this is the attention mechanism behind the transformer. There's a mask. This mask is to allow the word to pay attention to the previous input. And you can adjust the mask to allow the word can only pay attention to the word which is the previous prefix in the same path. And after you use this approach to do the fine-tuning, probably you will get slightly better performance and allow this model to fit the ASR lattice as the input, then which can be better for spoken language. And another work trying to use the spoken contextual embedding. The idea is because we want to build the embedding for each word, right? But this word is from the spoken. So that's just like we want to make this element to listen to the input, not only see the input. So if we have the ground truth transcript, show me the fares from Dallas to Boston, and the speech recognition output show me a phrase from Dallas to Boston. We want to have very similar embedding between a fare and fares, so that if we use this embedding from this model, which have a similar embedding as the gold standard output, it means we need to consider the acoustic confusion and trying to adapt the word embedding model to the acoustic domain. Then we can directly take the ASR output and apply this spoken element. Then we will have very similar embedding as the gold standard output. Definitely you can do it in the unsupervised way if you have this acoustic confusion from the unsupervised model, from the speech recognition. You can also build an embedding which have similar embedding for flight and lights. Then after you use the embedding for this spoken element, then you will have very similar embedding as the gold standard output. And it shows that they also have a better performance, especially your speech recognition is not quite good. In the linked model understanding, a linked understanding component, usually we do some evaluation. The metric include like two type of metric. The first one is we want to measure the intent prediction accuracy or the slot information, because usually we'll treat each sentence to only have one intent, so we can measure the intent accuracy. But if you have like multiple intent in the same utterance, you can use the intent F measure. And we have multiple slots in a single sentence, so slot should be measured in the F measure. And another metric is more is more difficult, which is the sentence level. That means we need to have the whole frame all correct. Then we will treat this sentence have the correct semantics. So we need to have a correct intent, and all slots should be correct extracted. After we go through the linked understanding, the next part we want to decide how can we track the dialogue state in the dialogue management. This is an example. The right-hand side are the utterance from the system, from the agent side. And the left-hand part is the utterance from the user side. Okay? So after the linked understanding, we can extract the semantics corresponding to each input from the user side. Okay? So dialogue state tracking is to track the current dialogue situation during the whole conversation, which means we need to merge the semantics and then decide what kind of information the user already provides us, and so that the following action we can decide how to respond to the user. Let's take a very simple example. In the beginning of the conversation, you can imagine you start with this null state, like not any constraint the user provide. So after user say the first sentence, find a good eating place for Taiwanese food. This example is the same as the previous conversation. And we will know that the user provide constraint about rating and type. So this dialogue state, after this sentence, will proceed to this dialogue state. Okay? And after the next sentence, the user said, I want it near to my office. So probably they add additional constraint about the location. So ideally, you will find that the current dialogue state is at here. Okay? It includes rating, type, and location. So this is the perfect path for this dialogue state transition. For this two-sentence conversation, it seems very simple. However, deliver this correct path and tracking this path correctly is very, very difficult. Let's consider a situation. Find a good eating place for transport. It speaks very quickly, so this is the correct semantics. However, due to the speech recognition error, you may recognize Taiwanese food as Thai food. So you will extract the type is equal to Thai. In this example, you will think there's no additional problem. You can also track the same dialogue state here, right? Because we extract the rating and type. But actually, you need to decide the type is equal to Thai or type is equal to Taiwanese. If you assume the incorrect dialogue state, then your return list will totally wrong because you ask for Taiwanese restaurant, but you provide the user several Thai food. Then the user may not satisfy with your service. So here comes the problem due to the recognition error. But also, the previous component is the link. Do you have any question?
Can I? Yeah.
Yeah.
Can I? Sorry, I'm a bit lost about how you combine the dialogue part that you do, maybe neural network based, with all this kind of more symbolic information. Is that okay? Nice.
Okay, you mean how to extract the symbolic part from the natural language?
How does the because we saw one system that does everything end to end, right? Like it uses embeddings to decode information that was already given by the user. But in this case, you have this graph representation of constraints. How does the system combine and use this symbolic information or graph-based information with the information that is being exchanged during the processing of the language itself?
You mean how to merge the information, consider a dialogue state, right?
Yeah, how does the system, suppose you have the conversation and then, does the question make sense, or Andreas, yeah?
Right. I want to give you an example how dialogue state tracking is performed. So we describe this first, and we will see how to merge the semantic during the conversation. Okay, so that dialogue state, we want to do dialogue state tracking is we need to combine these semantics so that we can decide which is the best action to interact with the user, right? So here, we want to describe the difficulty about dialogue state tracking. Okay, is it okay? And we will continue how we track the dialogue state. Okay. So, because the previous information for this symbolic semantics come from the language understanding. So language understanding is not perfect, so they may produce some error. For example, sometimes you only extract the rating information without type information. So in this scenario, you will assume the current dialog state is here, not here. But actually, the correct one is here. So only one sentence, you will have multiple noise from recognition error or understanding error. During the whole conversation, you have multiple sentences, and you need to merge so many information together and also consider the noise from each utterance, which is very difficult. That's why dialogue state tracking is not, it's also not solved yet, and also very difficult to address. And let's look at the one example. Dialogue state tracking can help us to improve our understanding. As we mentioned, book a table for 5. 5 is the ambiguous term, right? In the beginning, we know 5 may be number of people or time information. And we have the value equal to 5 for both slots. And we also have like 0.5 confidence for these 2 slots. Okay, so if we do the dialogue state tracking, after the next turn, how many people? And we know the people information is equal to 3. And this recognition confidence, they provide us 0.8 confidence. So we can update this value is equal to 3 with higher confidence score. And also because we track the information for time, so this information can be also updated as the 0.8 confidence. If we only extract the semantic and directly merge it together, we cannot have the dialogue state tracking just like this example. Because we know number of people and time information are aligned together, so if we have higher confidence to believe number of people is equal to 3, it means we need to believe we need to have higher confidence the time information is equal to 5. Just like a human. As a human, we can easily decide that, but in a machine, it's very difficult to track this information coherently. Here is another example for multi-domain state tracking. So this user wants to purchase a movie ticket, Okay, so based on this sentence, we will extract the semantics. Like movie, they have the date, and they do not have the time information yet. They only tell me they want to do it tonight. So we have a time information with lower probability. And they have 2 people, and theater location is assigned. Okay, so after you ask the additional information, and you find out the user want to have the dinner first, and then go to see the movie. So they want you to check what the availability in this restaurant, and you will find that the restaurant information, the earliest time is 6 p.m. So you will automatically update the information for 6:30 p.m. has lower likelihood. The reason is it almost impossible to go to see the movie in time if you need to have the restaurant. You need to have a dinner in this restaurant, because only 3-minute time is not enough. So you will automatically update the confidence, like probability, for this slot slightly lower. And after several interactions, you will finally decide the time information for restaurant is 6, and movie information you can do it in 7:30. So you need to track both information coherently and trying to update the value information and consider their probability. So it is very complex. Although the behavior is very complex, but the model itself is relatively easy, because you just imagine we want to track the dialog state, right? So we call it DST, dialog state tracking. If we want to decide the current state for this turn, okay, how to do that? We just extract a lot of features from previous history. You can include like semantics, you can include the natural language context, and directly put all information to the model. And your output is supervised. Your output is the slot value distribution, which is the dialog state. So your goal is based on previous history, including like semantics and natural language. Your goal is trying to generate the correct dialog state. So dialog state means you have the slot value distribution for each slot, just like previous example. So here is a very common classical model delivered by Cambridge. It uses Onion to do the dialog state tracking and use CNN to extract the sentence level information. The reason to use recurrent neural net is they consider dialog state as the temporal information, because the current dialog state will be relevant to the previous dialog state. So you can use Onion to model the temporal information. Each white node includes the user turn and the system turn, like 2 sentences. And you need to output the dialog state corresponding to the current turn. And you will model the whole conversation together based on the several dialog state labels. And for the user turn and assistant turn, this model uses a very simple CNN to extract the embedding. And they will also train in end-to-end manner, including the CNN and the whole Onion. So one sample is one conversation containing a lot of dialog turn and a lot of dialog state. And this is a modification for the previous model. It include the candidate from the database. Because if you track the information, you need to consider the current database information so that you can have a better understanding which information is more possible. So including the candidate from database, you will get slightly better result. And these days, there are a lot of variation for dialog state tracking. And this is especially interesting, they consider to use two modules. One is the global module. It includes the information for all slots. They want to have shared information. And also, local module learn slot-specific information. So just like very advanced encoder to encode the previous context and trying to deliver it for different slots. So the shared model, the global model, will have a shared information across different slots. So if you are interested in dialog state tracking, you can see this benchmark data from DSTC. And DSTC, until now, it's already DSTC 8, but they changed the name. Originally, it called Dialog State Tracking Challenge, but they changed the name to Dialog System Technology Challenge. So until DSTC 6, they contain multiple tasks, not only specifically for dialog state tracking, but DSTC 1 to DSTC 5 only focus on dialog state tracking. So you can check the data and to see how they label this data and how can we provide it for track the correct dialog state. This is one example from DSTC 4 and 5. And this data is the human-human conversation. They want to track the dialog state based on a partial conversation. For example, this is the partial conversation. After seeing this conversation, you need to design the current dialog state. And current dialog state include like the this user considered to have the hotel information, and the hotel should be like the hostel type, and so on. So you want to track the dialog state based on the part of conversation. In this part, our goal for the evaluation, we want to track the correct dialog state, right? So you can track and you can measure whether the tracked state is correct, corresponding to the gold standard dialog state. And also you can track for each slot whether you have the correct information or not. So you can measure the recall precision and F measure for each slot, because each slot need to have their own value to be tracked in the whole conversation. And also, why we want to track the dialog state? Actually, the dialog management want to design a final system action based on the tracked state. The reason is, this is the same example as previous one. Based on the dialog state, for example here, the agent need to decide, oh, at this stage, we want to inform you something, or we want to request additional constraint. This is the dialog policy, which is we need to design a system action so that to interact with the user. So we call dialog policy optimization. This is the main part for the dialog management. They need to track currently, the current conversation provides some type of information, and what kind of action we need to interact with the user, which is the agent's brain. So now we need to describe a little bit for reinforcement learning. I think you all know reinforcement learning, but why reinforcement learning is applied in this area? Because usually we use supervised learning for a lot of tasks. That means if we want to train an agent, we need to have a supervised information. Based on the input, we need to provide an output. Then we can collect a lot of pair of input and output and to train this agent. However, in the real scenario, you cannot enumerate all possible input and output. So after you supervise train this agent, you need to allow this agent to interact with the customer by their own. which is reinforcement learning. After interact with this user several times, and after the conversation, this customer get angry. So this agent need to slightly modify their conversation strategy, but they do not know which action is not correct. Just like you play the Go game, and you don't know which move is the best move at the current stage. The only signal you can get is after the game. You lose again, and you will get the negative reward. So you will try to update your policy. So the supervised learning, just like you want to learn the policy, like the action from teacher, you have a supervisor. They tell you, given this input, you need to have this output. However, in the real scenario, you need to learn from critics because you cannot enumerate all possible input and output. It's an interactive environment. So we can formulate dialogue manager in a reinforcement learning framework. User will say something in the beginning, and understanding component will provide us some semantics. And dialogue manager need to decide an action to the natural language generation, and then get back to the user. And this is the interaction between the agent and the environment. The user can be viewed as environment in this framework. Based on the observation, like semantic generate from the understanding component, we need to decide what is the best action in order to maximize the reward. And until now, if we can formulate this task as a reinforcement learning framework, it means we want to allow our agent to select the best action. And this best action means this action can maximize the future reward, like future expected reward. Okay? So then we can apply any reinforcement learning approach to learn how to interact with the user. So the first question is, how can we design the reward? It's unlike the game playing. We can directly use the score for this game as the reward. So in a dialogue system, dialogue is a very special reinforcement learning task because the reward should be decided as how you measure your system. This system is a human-in-the-loop framework because the human will be the environment. It involves the interaction and the rating for a dialogue. So if we want to use the reward and treat as an evaluation of our system as a reward to learn our reinforcement learning agent, we need to consider, for example, the conversation is correct or appropriate and adequacy, a lot of information for the whole conversation, and use it as a reward to teach our reinforcement learning agent. This is very difficult. The reason is, how can we get this rating? Is it possible to get the rating from expert? It could be possible, but it will cost a lot because you need to ask a lot of experts to annotate each conversation for you, and you apply the reinforcement learning to learn your agent. And it's kind of impossible. And another one is you collect the rating from user. You just ask user, oh, what do you think about this conversation? Give me the rating. And the cost is median, but sometimes the quality is unreliable because sometimes the user just randomly pick a score, or sometimes they do not want to provide a score. And another alternation is we can try to have the objective rating. For example, we can check some desired aspect, and check this information do not require additional annotators, so the cost is lowest. So how to do that? Usually, because we focus on task-oriented system, right? So we can check whether this task is successful or not. For example, if this is a movie ticket booking system, and we check whether the final ticket is purchased by the user or not. If the user decides to purchase the ticket and we treat this conversation as successful, and then we provide, for example, a positive reward for the reinforcement learning agent. And also, we need to penalize the longer conversation because we want our conversation to be successful, but we don't want to have very long conversation. So usually, for example, we will have, if this conversation is successful, then this system will get 30 as a positive reward. And we will penalize the system if they use additional turn to do the interaction. So in order to maximize the final expected reward, they were trying to make this conversation successful and as soon as possible so that they can have they can maximize the final reward. This is the work from Microsoft Research. They're trying to use the reinforcement learning plus.
I have a question that maybe it's a little bit further in the exploration of these models, but you said that we can use the reinforcement learning for the task, and of course it sounds reasonable, but I have this kind of a doubt that also you said the objective, that is, I also agree that is very, very good metrics for that, but at some papers do we see this kind of the side effect that, for example, let's assume that we are talking about this system to book a movie theater, and we know that the machine learning can be very smart and very lazy at the same time. So he can just try to learn that if the user will say, all right, I want to go to the movie X today, the model will say, all right, so you need to be hurry because the last time they are playing hour from this time. But it will be the delay because we have, for example, 3 movies today. And as I understand, the user already paid for this ticket, so this objective rating will be very high because at first the conversation was very, very short because the model said you need to be hurry, buy your ticket now because this is the last chance for you. And also, so the conversation was short and the user buy the ticket. So do we have any other things to prevent this kind of events when the machine learning, the reinforcement model will be smart and lazy at the same time and can even lie to you just to have that effect?
I see. Like the main concern for this type of system is we want to use reinforcement learning in order to model the noise from the system. The reason is sometimes you do not, the information is unsure. Like you have the information, but they have some misrecognition or the error from understanding. So if we directly take this information and provide a ticket to the user, this ticket may not be correct, and the user may not accept this ticket in the end. So you will have a value and you will have a negative reward. And the system need to learn if our information currently is not is unconfirmed, then we will try to ask more confirmation question to make sure this information is confirmed. Then we can have a successful conversation. So they need to try to balance between efficiency and also the ensured information. So they're trying to learn this behavior because the dialogue management don't know which information is correct or not. They're trying to model this noisy scenario.
Thank you very much.
Okay.
I would have a further question related to that. So when you talk about the noisy environment, so if you consider like a real chat or whatever, you talk to your boyfriend or a girlfriend and she changes her mind, so no, make it Chinese. So, well, I'll be okay with Thai, it's good enough, and something like that. So it's all gets more and more confused in the model, and that would be in some sense realistic. And I think that it is really a complication. I haven't looked at the test sets. I went to the web page, and it's nice that there are test sets for this kind of thing, but this is definitely an extra complication for this kind of model, right?
Right. And also, there's also another issue, which is for reinforcement learning interacting with the game, we will have a game simulator, right? But in the dialogue system, we need to have an environment which is a user. So we need to have a user to standing there and to interact with our system so that we can apply reinforcement learning with this user. And it's very difficult because no real user will have enough patience to interact with your pool system. And the user will just give up. Then you do not have a good system a good user to interact with. So the first question, the first issue is, how is it possible to build a machine just like a user? And we learn from we call it user simulator, and we use this user simulator to train our initial dialogue agent. Then we apply to the real user and trying to fine-tune our policy with the real user. So this is the current ideal approach, but it's also difficult. So you will see this approach is trying to build a neural dialogue system in the right-hand side, and also build a user simulator in the left-hand side. So the user simulator should not be the same as the dialogue system, because user simulation, the user will have their own goal. And the dialogue agent is trying to help the user to finish the goal. So they have different behavior. So you need to model it in different way. So the left-hand side is you can also write a rule-based user simulator, or you can just use the machine learning to learn a user simulator to mimic some type of user. But ideal goal is no matter what kind of user interact with this system, the system can have the adaptability to adapt to this scenario. So this approach, ideally, is we use the supervised learning to train each component, for example, understanding and state tracking. And then we concatenate all pipeline together and to enable reinforcement learning based on the interaction between user simulator and neural dialogue system. And we are trying to learn which is the best action in order to maximize the reward. Although a lot of people will criticize this, user simulator is not the real user, but this is it's also very difficult. The reason is we do not have a real user to interact with. So this is the current difficulty for dialogue system area. But you can see some progress for this area. Using reinforcement learning, we compare with the rule-based system. And in the rule-based system, usually you will ask several constraints one by one, or you have a list of priority. And you will see that for this user, some information are not important at all. So after you interact with this type of system several times, they will automatically figure out what kind of information needs to be asked first, and trying to make the conversation more efficient. And the idea is, for example, one customer always care about location, and another customer always care about price. If you are a smart agent, you interact with both of them several times. And next time, the first user who care about the location come to you, and you will ask, oh, do you have a location constraint first? And another person, for the person who care about the price, you will ask the price constraint first, and you will adapt their interaction behavior, and you will have a better conversation, which is more efficient and also can be successful. So idea is use reinforcement learning to learn how to have a better interaction and to improve the efficiency. And also, using reinforcement learning is very difficult. The reason is reinforcement learning need to have a lot of sample, right? So which is a sample inefficient approach. And also, a lot of people will criticize if you interact with the simulator, which is different from real user. So this is the approach from previous slide. We have a conversational data collected offline, and we use the imitation learning to learn the policy. Then, the idea is we want to interact with the real user and apply the reinforcement learning, right? But this cycle is very difficult to learn. The reason is we need a lot of conversation in order to update the models once. And the user may not have enough patience to do that. So how can we address this issue? We can consider to learn the real user behavior and use this model to do the planning first, which means when we do the interaction with the real user, this real experiment can be used to learn a word model. It's supervised learning. This word model just trying to provide the policy model a fake experience. So they just generate an experience for the policy model. So the policy model will have more sample to do the update. So it means you can only interact with the real user once and get some fake experience from the word model, maybe 4 times. Then you will have 5 times more sample to do the reinforcement learning. It may boost your performance in the early stage. So this paper, it shows that the blue line is the original DQM model, like a basic reinforcement learning model. During the interaction, they will have better and better success rate. And the green line is DDQ2, which means you interact with the real user once, and you collect 1 fake experience from the word model. So you will see the green line will improve the performance, especially in the early stage, because using reinforcement learning, usually in the beginning of the learning, the performance will be pretty low. So if you can get more sample to do the update, you can quickly improve the performance with the same interaction turn with the real user. And so you will think if you can interact with real user once and several times from the fake user, like word model, we can get more fake experience to improve our performance. So if you use DDQ20, it means you only interact with the real user once and 19 from the word model. And you will see that sometimes the behavior, like the learning path, is unstable. The reason is this policy learning will suffer from the poor quality of the fake experience, because fake experience may not similar to the real experience. So if you interact with the fake experience too many times, then your policy will be degraded. So you need to have a good balance between the good one and the fake one. So how about we add a discriminator to help us to filter out the bad experience? Just like the same framework, but we add additional discriminator to control the quality of the planning experience. So adding this discriminator, you will see the better result. The red one is the adding the discriminator, and the DDQ, which is the purple line, you will see in the beginning of the interaction, adding the discriminator will control the better quality so that they can boost the performance a lot. And what is the green line? Green line is original DQN, but it interact with a real user 5 times. So it means you need to have 5 times cost to interact with the real user. So it almost approach to this upper bound using discriminator, adding to your framework. And this work also show that the D3Q have a better performance than DDQ and DQN for human evaluation. So we think we need to learn the policy not only from the simulator, but also from the real user, so we can easily adapt to the real scenario. So the current research community consider that we need to have an environment which we can interact with a real user, but this slightly difficult because the company may not provide you to interact with a real user, and as a university researcher, they do not have the real user to interact with. We only have like small society as our user. So, which is the difficulty to directly applying to the real scenario. So in a dialogue manager, we know we need to track the dialogue state first, and then decide which is the best interaction to do the conversation. So we can measure whether this system accuracy is good or not. But it's very difficult because sometimes we do not have a gold standard system action, and sometimes if you choose another one, but probably you will have a better conversation in the end. So use the turn level evaluation may not be very realistic. So usually we'll also have the dialogue level evaluation. Based on the whole dialogue, we can measure whether this conversation is successful or not. And we can also consider the reward, because reward contains the success rate and also the efficiency of the conversation. And if you are interested in the dialogue management part, Microsoft provides data including 3 domains, movie ticket and restaurant and taxi. And they also provide a user simulator. But in this data, the user simulator are not very good, but you can also build your own user simulator to interact with. But they have the data annotated with the slot, intent, and also each system action. So I think it's pretty good.
I wanted to ask just, this is a very complex problem, and have there been attempts to just restrict the user to use some sort of simple language? For example, if you want to book a restaurant, you have to use specific syntactic structure, because for every interface we are trained to use them, keyboards, mouse, so why not train the user to just use some simple language in order to greatly improve the accuracy of the dialogue system?
Oh, this is a very good question. Because the user may not know the backend system, so they don't know which information you need in order to get the return information. So they can only say something about their goal. So the agent needs to extract the semantic which related to the backend system in order to search the information for the user. So the user don't know what kind of backend you will have. They don't know they need to provide like location and provide maybe the movie name or something. They don't know what information you need in order to query the database.
Yeah, but then the system would train the user. It would say, I don't understand you, use sentences like this, for example.
Oh, I see. This is also a very good issue. A lot of people debating about because the user will be trained based on this interaction, right? So they will understand, oh, they can only say something and the system can understand. But our goal is we want to build a system trying to understand the user's language. Not the user need to speak something which can be understandable by the system. So which is a very difficult problem, just like chicken egg. And because the user will be affected by the system, but the system trying to understand the user. So we hope the system don't change the user language. The user just use their own language, and the system will try to help the user and trying to understand the language originally from the user. Right? Did I answer your question?
Thank you.
Okay, let's continue. And previously, I forgot to mention, you are feel free to ask any question in the middle of the lecture, and I will check each part whether you understand it well, and then continue. Okay. So, just briefly review. Previously, we do the understanding in the beginning to extract the semantic based on the sentence. And then the dialogue manager needs to track the dialogue state in the whole conversation. And then this dialogue state helps the dialogue policy to decide what kind of system action is the best one in order to maximize the whole conversation interaction, like maximize the reward. The reward, usually we want to maximize the user's satisfaction, so we need to have a simulator user to provide us whether this conversation is good or not. So how to build this simulated user and how to do this interaction is very tricky, and also a lot of debating and a lot of limitation for the research community. And in the current product, you will see that the current product do not have the reinforcement learning-based dialogue management. The reason is if you directly enable the machine learning for the dialogue management, you cannot control the system action. And for the company perspective, they want to control the action, so the system may not say anything which is not proper for the situation. So usually in the current product you saw right now, almost all based on the rule-based dialogue policy. For example, you can write down a big tree structure and to decide what kind of dialogue state, and you need to do some specific response and use this tree structure and to fix in the dialogue management. But ideally, we want our model to explore by themselves and trying to find a good policy which is better to optimize the conversation. So here is the mismatch between the research community and the industry. So that's also move on the next component, which is the generation part. The generation is the opposite way for the dialogue and then language understanding. Just like we want to base on the semantics to generate the corresponding natural language. For example, given this semantic frame, we want to generate a corresponding natural language. And you can imagine we have very simple way, which is we can build a lot of template-based NLG, just like the current dialogue system. You can just allow a lot of experts to write down a lot of rules to map the frames to the natural language. And the pros include, this approach is very simple. You just need to have the expert to write down the rule. And it's error-free. The sentence will be grammatically correct and easy to control. They will not speak anything which is unproper to the situation. And also, the cons include it's time consuming, and it's a little bit difficult to scalable to other domain. If you want to extend to another domain, you need to hire another expert to write down this template for you. So definitely we can use some machine learning approach to do the generation. And this is the very simple way we do the linked model generation. And previous lecture, you already know how to build a linked model. And similarly, we can use the linked model to build a language generation system. And this language generation system should be conditioned on the given semantics. So for example, you need to have the input here, and we can directly take the output and to do the delexicalization. The reason to do the delexicalization is we want our output to focus on the semantic, like the slot level, not the surface level. For example, this is the restaurant name, 鼎泰丰, and this is the type, and we want to delexicalize it as the restaurant name and also the food type. After we do the delexicalization, this generation model will learn how to generate the information which is related to type, not only for Taiwanese itself. So we need to do the delexicalization for the output side, and then for the input side, we just build a very simple one-hot representation for dialogue add. What does it mean? You can imagine, for example, if we have like 5 different intent, then each one indicate a certain intent. So for example, this dimension indicate inform. So we can have one indicate this inform. And we have multiple slots. And these 2 slots include the information. So we have 2, 1 here, indicate name and food. So given this one-hot representation, we need to generate the corresponding sentence. So it's very simple. We just collect a lot of semantics and corresponding natural language. After delexicalization and one-hot encoding, we can learn this NLG in a supervised way, okay, which is very simple. But this semantic condition generation has some issue. This issue is about semantic repetition. You will see that this is some output example. 鼎泰丰 is a child-friendly restaurant and also allows kids. And these 2 information are the same. But why they generate it again and again? The reason is when you train this model can only generate the information based on this vector. But in the next word, they don't know what information is already been generated. So they also see the same vector as a condition. So what they're trying to cover the information again and again. So they will repeat the same semantics. The semantics from the input in representation. Because the condition is the same. They do not update the condition information, so they will try to repeat their semantics. So you can imagine we can use some, for example, attention mechanism or some gating mechanism to address this issue. So this is an approach, very simple. When you do the LSTM for generating each word, ideally, if this semantics is generated, then this vector should be updated. 1 should be decreasing to maybe about 0 if we already generate like food information. So we can use an additional gate to control the LSTM so that in the next generation turn, they will see the different condition. The condition may not include the same semantic, which is already been generated. Then all model will be trained in end-to-end manner. They will automatically update what kind of vectors should be updated, and so that we may not have the repeated semantics. So the take-home message is we just use very simple gating mechanism to control the semantics which to be generated. And we want to automatically update the condition in the vector. However, the current NLG system in Dialog has a lot of issues. For example, the natural language generation, it tends to generate shorter sentence. And also, sometimes they will generate grammatically incorrect sentence because we just use the Airman to do the generation, right? So we cannot control we cannot check whether this grammatic is incorrect or not. So let's consider how children learn to speak. If you are a child, you will sometimes speak some simple content word first. For example, if you want to go to the toilet, you will say, "Daddy, toilet." Only these two words. And if you go out a little bit, you will add like more words like "go to toilet," and finally you will figure out how to make the whole sentence grammatically correct. I want to go to the toilet. So how about we consider this linguistic pattern as a human? We can generate word pattern in a specific order. It's a very simple idea. Just in the generation part, generation is the decoder. We decompose the decoder into several layers. Like first layer only focus on generating the content word like for noun. And afterwards, we just allow this layer to focus on adding the verb information and adding the adjective, and finally, it will make the whole sentence grammatically maybe better. So in this way, it's better to generate a longer sentence and also probably grammatically correct. And the idea is, in the decoder side, we separate the drops for each layer. So we can have like small, maybe similar size of the decoder, but with a better performance in terms of the length of the sentence and grammatically correct. Definitely you need to add some tricks in the decoder side. Okay. So in the natural language generation, to do the evaluation, which is very, very difficult task, there are a lot of issues about generation evaluation. The reason is usually the best metric is human judgment, because only human can make the judgment whether this sentence is good or not for a current situation, right? It includes, we need to check whether the meaning is correct or not, and whether the linguistic is fluent or not, and whether the readability of this sentence based on the context, and also the diversity of the output. So all information should be considered in order to give a rating for the current generation sentence. But if you are working on the generation in the research community, it's very difficult to get the human judgment. So there's some approximation to have like objective metrics. For example, as just like machine translation, a lot of people use blue score, but blue score consider like your generated output and the gold standard output, like the how much ratio of the word are overlap between each other. But sometimes, if you do not have any word overlapping with the gold standard output, but this semantically is still correct, so we also want to consider this situation, but the blue score or like some rose score cannot give you this good measure. So this is an approximation, but this approximation may not be perfect. So a lot of people consider whether we can use some word embedding, because the embedding is supposed to have the semantic information, and we check the semantic, whether this similar to the similarity between your generated output and the gold standard output. But if you consider a dialogue, you may have a lot of different type of output, which can be viewed as the correct or proper output. So in the generation area, the evaluation is always an issue. And a lot of researchers are debating how can we have a better metric to do the evaluation. But still, probably currently we do not have a good answer for generation evaluation. So basically, in the generation work, they will include both objective metric and also subjective metric. And objective metric, if you consider the language like surface from overlapping, you can use blue score or Roche. But if you want it to contain, for example, some knowledge, you can check the desired aspect and to have an additional metric. And usually in the generation evaluation, they will have a very big table, including different type of evaluation, like human evaluation and automatic evaluation. And hope you can use this different type of evaluation to convince the reviewer that your approach is better than the previous approach. So this is how current research community work. The reason is a lot of research work show that there's a gap between the human perception and the automatic metric. But there's no good solution now. So the only way is show both. Then you can better convince the readers. Okay, so do you have any question about the generation part?
Yeah, I was wondering whether the semantic frame has to be the same as the one that was used when decoding the utterance, like when we saw at the beginning the whole pipeline, we started talking about the semantic frame, but the semantic frame that you use for natural language generation, you also you have to have the same semantic frame, right?
Yes, because this part is about task-oriented dialogue, right? So you need to remember we will have a database to search. So the database provides you the ontology. For example, if there's a restaurant, they will have the corresponding attribute. And you can only cover the attribute stored by this database. So if it's impossible to, if you add the additional attribute which is not stored in the database, the agent cannot answer this question, right? So it's always need to align with your backend database. So in the generation part, the intent, like the slot is the same as the input because the user may have the concern about the slot. And the agent needs to also provide the information based on the slot as well. But you will have, sometimes you will have the flexibility. For example, sometimes the user may not have some request about the slot constraint. But the system side, the agents need to provide this information because some slots are not requestable, and they will have a different definition about the slot. For example, you may not know the actual address about the restaurant, but the agent needs to provide you this information, right? In the beginning, you only say, oh, I want the restaurant nearby somewhere, but you don't know the actual address. But the actual address may be stored in the database, so the agent can provide this information. So there's some mismatch between the agent semantics and also the user semantics.
Okay. So whether the system decides to inform given some variables that were given in the query, how I still don't understand how the system decides, like, okay, these are enough keys for me to give an output. And when it gives an output, how does it decide which information will it give, given that, okay, you can make a later on question, like, oh, okay, nice, you made the reservation, can you give me the address? But sometimes it does it by itself. But so
Okay.
when it decides to inform, and how does it select the keys that it like? It doesn't always have to provide the same keys, right? It's just the system that decides.
Right. So there's two parts. One is generation only. So generation only need to focus on generating the natural language given the semantics. So your question is about how can we design what kind of semantic frame we need to respond to the user, right? So usually in the dialogue policy part, we will have like 3 types of the action. Like first one is request. Like the agent want to request additional constraint. And the second one is inform. We want to inform like the current situation to the user. And the third one is also very important, which is confirm whether the previous information is correct or not. So usually we have these 3 types of action and align with a lot of different slots. For example, if we design to confirm, we need to design what kind of slot we need to confirm, right? So there are so many system action to choose in the dialogue policy. So the reinforcement learning is trying to select a best action in order to maximize the final reward. So for example, if you design, currently we only confirm this, we request this 2 slots. Probably request like 3 slots is better. And if you only request 2 slots and in the next turn you need to request additional one, and it just wastes an additional turn. But if you request like 10 slots in the one single sentence, the user may not respond to you because it's not realistic. It's impossible to answer so many information in the same time. So the system needs to balance between what kind of information to choose, like the action, and also consider the final reward. So this is only for dialogue management. So dialogue management, you can consider which is only operate by the semantic level. So it can work for any language because they only consider semantic level. And natural language generation, trying to map the semantic into natural language. So you can have like universal dialogue management, work for different type of language, and understanding part map the natural language to the semantic. And then generation map the semantic to the natural language. So the dialogue management can operate in the semantic level only.
Okay, thank you.
No problem. Other questions? Okay. Then it seems that we covered the whole framework about task-oriented dialogue. And usually you'll see this evolution roadmap from by two directions. The first direction in the axis is dialogue breadth, which is about coverage. Now currently, we consider to build a system for a single domain. For example, we only purchase the movie ticket, or we only book the restaurant. We build 2 different systems to work for these 2 different domains. But if we build a system for one domain, is it possible to extend to other domain and trying to have a single system to work for multiple domains? For example, if you imagine you have a Travis, which can help you to book the ticket and also book the table as well. So you want your system can be multi-domain or open domain, like any domain it should be able to handle. So which is the coverage of the dialogue system. But if you consider what domain is, the domain is aligned with the database. So in the beginning, we need to design what kind of database you need to search, right? So which is related to the domain. So if you want to have an open domain system, that means you don't want to design a domain, so you cannot search the database. If you do not search a database, then you don't need the intermediate output to build a query and then get an answer from the database. You can directly treat the whole system as a statistical model, like a neural network, just based on input. Then we're trying to generate output. But in this scenario, this model cannot connect to the database. So some scenario, it cannot use this part to do some specific scenario. The reason is some information will be dynamically changed. For example, today's weather. You always need to check the database and to call some API to get the weather information. And sometimes, for example, you want to book the table, you need to check the current availability. So you always need to search some database. But some type of information, you don't need to. Some information is not dynamically changed. For example, some factual information or like some greeting, hi, how are you? This type of things, you don't need to search the database. So that's why a lot of people working on social chit-chat trying to use this end-to-end model to generate output given the input. Then the approach is the same as machine translation. Because machine translation just given the input from a source language, trying to generate the output from the target language. Then we can treat as the same framework, given the conversation history. The goal is trying to generate a response. Then we can use the sequence-to-sequence model, like encoder and decoder model, to train this neural response generation. So in this framework, you only need to collect a lot of conversation and treat the previous sentence as the input and the next sentence as the output to train this model. This model trying to select the target sentence, which has the maximum probability given the source sentence. It's trying to maximize this objective. And the good thing for this model is we can directly collect a lot of conversation without any annotation. We don't need to annotate the dialogue state. We don't need to annotate the action and intent and slot. We directly put it into our model and trying to learn how to do the generation. So a lot of people work on the chit-chat research trying to generate the output based on the previous input. And you can imagine if we collect a lot of script from movies, then it's supposed to learn how to generate the next sentence based on the previous movie scenes. So this is an interesting video, which is use the sequence model to generate the sentence and use it. And the data is from a lot of different type of movies, and they directly learn this sequence model to generate the next sentence. So that in the beginning, you just feed the first sentence or feed nothing, and it will generate the second sentence, and the second sentence as an input to generate the third sentence, and so on. And then you will have a whole movie. Then they just add like some visual things to make you feel it's like a movie. And we'll play the short clip from this video. And note that the caption in this movie is the automatic speech recognition, so there's a lot of error. So just pay attention to the audio.
Go to the skull. I don't know.
What do you mean?
Well, I don't know anything about any of this, so.
Then what?
There's no answer.
We're going to see the money.
All right.
Okay. I only extract the small segment. If you are interested in the whole movie, you can check the link. So what do you think about the movie? Actually, after a lot of people saw this movie, they think we don't know what information this movie wants to deliver, but the conversation seems natural. It's okay. It's not very weird, but just we don't know what this movie is about, right? The reason is a machine is so smart. It learned how to generate the output, which is reasonable, but which is not specific for the current input. For example, you can say, I don't know for any type of input, because if you remember the previous objective function is given the input, we want to select the target sentence, which is the maximum probability given the input. So the machine learns this type of general response always have the higher probability, no matter what kind of the input is. So if you directly train this model, you will find that like 30% of response are very general and meaningless. For example, I don't know. I don't know what you are talking about, this type of things. And it seems reasonable, but it's meaningless. It's not what we want. So how to address this problem? Like previous approach, trying to address this issue, they use the mutual information. This is the mutual information objective. So if you look at this equation and to expand it, you will find, oh, this is the standard likelihood, just like previous approach. Given the source, we want to maximize the target sentence, right? So you need to consider like another side. So they slightly modify the later term so that your model not only maximizes the first turn, but also the next turn, which is given the target. We need to also recover what kind of the source sentence is. That means you cannot generate very general output, because the general output as a target, given this target, you don't know what kind of the source sentence is. So just add a very simple trick in your objective function. Then you can have better response. So you will see the same input, and currently they will have slightly better output. Previous approach, they only generate, of course. And here, it will generate, of course you can, because the input question include, can I have one? So they will have like better association between the input and output. And also, they say they are delicious, because the input contains some information like make your mouth water. So they will have like topically related output corresponding to the input. So adding this simple trick, you may have like slightly better like topical related output for your generation. However, the conversation usually lies in the real world. So not only the language itself is important, other information, for example, multimodality, are also important. For example, if you do the conversation, you will also have the information about like another person's face, and you will have a visual signal. And sometimes you will know the persona of this person, and you also have your own persona. So you will have different interaction appearing in the conversation based on this different type of modality. But if you only collect the language part and trying to learn the system to generate the conversation based on language, it's not enough. So that's why a lot of people trying to use multimodality to do dialogue system. For example, you can collect like visual information and to recognize the emotion, or trying to extract your brain signal to help to understand the current intent or the current information. Because not only language itself, other information are also important. Let's see the one example. If we do not consider this different type of multimodality, you will see very weird, inconsistent response. For example, if the user asks, "How old are you?" the agent will respond, 16, and you. And then if you ask, "What's your age?" it will answer 18. Why? It seems inconsistent. The reason is your data is correct from different speakers, right? Different users. And you do not have the annotation about the data. So you don't know these two terms correspond to the same semantics. You can only maximize the target sentence given the input. So if you directly train this model, the model will automatically select the target sentence to generate, because they don't know this input sentence should be the same, and they need to generate a consistent output. But if you want to train your model use big data, you definitely need to collect the data from different users. Otherwise, you cannot train a better model. So how to address this issue? A very simple approach is we can add additional information in this sequence-to-sequence model. This is the basic sequence-to-sequence model, right? But in the decoder side, the output sentence may be generated by different users. So we want to incorporate the speaker information in this model. How you can do is you just build a speaker embedding. In the beginning, you just randomly initialize vector, and you allow the same speaker has the same embedding, and fit this speaker embedding into your decoding side. So during the decoding, the model will learn how to generate the sentence and also consider the speaker information. So in this way, we can also use the whole data for this single model, but the speaker information can be also considered by this model. And they will automatically learn, like if the two speakers have very similar embedding, probably it means they will have very similar, for example, living location, because they have similar output or similar personalization. This is the persona model's output. The left-hand side is the previous inconsistent response. And adding the speaker embedding, you will see that they will automatically correct the output, like the decoding side, with the same persona. No matter what kind of question you ask, they will always generate a consistent response. Like, what's your major? In the beginning, they will say business, and another one is say psychology. But here, no matter what kind of question sentence you will have, if they contain the same semantic, they will automatically design the same output for this stage. So this is one example to consider the multimodality. But you can imagine the conversation lies in the real world. So a lot of different modality need to be incorporated, not only the persona itself. You can also incorporate the visual and like a lot of type of information. That's why you will see the smart speaker. Sometimes like the new Airman Echo also have like a screen to, and also the camera to capture your face and trying to provide like better understanding based on the multimodality. However, until now, you find that this model is sequence model, right? So they only maximize, like optimize the output generation based on the turn level. Just like we only consider like one sentence, a single turn. But if you remember in the task-oriented dialog, although our dialog management designed the action for a single dialog turn, the ultimate goal is trying to optimize in the dialog level. Because in the task-oriented, we have a reward indicating whether this conversation is successful or not, and also the efficiency. How about we incorporate this information in the chit-chat side as well, trying to allow our model not only consider the single turn, but consider the whole conversation. But in the chit-chat, how can we measure the reward? The goal is we want to treat the engagement level as our reward. We hope this can be viewed as our reward to maximize. So how to design the engagement? The approximation of the engagement may be the length of the conversation. We hope if we have a longer conversation, it means the user may be more engaging in this interaction. But actually, it's not very true. So you can also like detect some emotion, whether this user is happy or not, as the reward and add it into your model. But if you directly use the length of the conversation as reward to fine-tune your sequence model, it will automatically learn that reinforcement learning agent, this is the original input. And this is the output by supervised model. And adding the reinforcement learning, trying to maximize the length of the conversation, it will automatically generate more interactive response. After they answer the question, they will add additional questions so that you can hand over the conversation to the user, and the user can say the next turn, and they will have a higher probability to have a longer conversation. So this is also the trick the human will use. So they will have like better interaction. So using this reinforcement trick, you may be able to optimize in a dialogue level, not only the dialogue turn. Okay.
Is the supervised learning agent using the engagement as a signal, or is it just percentage loss on the token level?
This is use the reinforcement learning, just like after the whole conversation, you will have the reward to measure this, what's the engagement level. And if you treat the length of conversation as a reward and to fine-tune your sequence model, then this is the reason.
But that's the array. What about the supervised one?
Oh, supervised learning is just the sequence model. So they only optimize to generate the target sentence.
I have one more question. So, well, let's say if we're taking into consideration the conversation length, the number of turns as the optimization, let's say, objective, what we want to maximize, then what happens? I mean, we have one human, at least in the loop, which is talking to a chatbot. What if that human is led, let's say, by his curiosity, and when they note that the chatbot is generating inconsistent response, they just brute forcing the same question again and again in order to see how many different or diverse replies they will get. Then this will probably saturate the results, because the conversation will tend to get longer and longer while the user is just playing with the chatbot, you know. So is there any trick to this to, let's say, distinguish between genuine engagement and just trolling the chatbot or playing like that?
Right, this is a very good question. It's also a very big issue. The reason they only use the length of a conversation is just like a very simple approximation. But definitely, you need to think about your own engagement, how to measure your engagement to treat it as a reward for your conversation. Because if you only consider the length of the conversation, it will happen, they just say a lot of unrelated things. So probably you want to check whether this whole conversation is coherent and topically related, and also like maybe length of each sentence may be considered as well. So you need to design your own strategy to measure the engagement. So in this paper, you can reference to this paper, and they will not only the length of the conversation, they also check some expert design like strategy. For example, they check whether the topical is similar to each other, and they will measure the coherence or some specific aspect, and then combine all information together, treat it as a reward. So definitely you need to design your own reward for learning based on the dialogue level. But this is the length of a conversation, just a very simple approximation. And in the
I was wondering if the fact that the array agent asks questions about, if that's essentially an exploration bias, like trying to get more to learn, or is it? So is it something that the RL trained agent does to actually get more out of human?
I think asking additional question may be a very simple trick, so that's why it's easily to discover. And maybe make more discussion about some topic is also another trick. So we hope the machine can automatically discover this different strategy to interact with the human. But definitely it's all related to how you measure the reward, how you judge, how you provide to the agent to maximize. If you only maximize the length, probably they can achieve the goal, but it's not align well with your original intent. So you need to consider both sides. And in the teachers area, I think the most successful dialogue agent is from Microsoft Research Asia, which is called Xiao. It's also the more open-ended chit-chat, and it focuses on, but it also includes a lot of skills. For example, you can send the image to Xiao, and they will comment something about this image, and you can also add some factual information. But the whole framework is trying to engage the user. And in that project, they use the, they can measure how many times the user interact with this system as a reward, and trying to use this to maximize the user engagement. So that's also a different perspective you need to consider. But the next issue is also very important. This issue is very difficult to address, especially in this end-to-end method. Because in this end-to-end social chit-chat, your knowledge, you do not have any grounding, which means, for example, the user said the weather is so depressing these days, although you just want to chat. The agent said, I know, I dislike rain too. Although this is only about chatting, but if this day is not the rainy day, this conversation seems very weird. So sometimes, if you only do the chatting, you also incorporate some knowledge in the conversation. But if you directly use this end-to-end model, you do not know what kind of weather for these days. So you don't know you need to generate like rain. or like cloudy or something. So how to move the social chit-chat slightly toward the knowledge-grounded conversation? It's a little bit like between social chat and task-oriented. Because task-oriented, they will have a fixed database to search for. But social chit-chat, they do not have. But sometimes you are in the middle. You do not have the database, like fixed database, but it also contains some knowledge you want to incorporate. So here comes a lot of work about knowledge-grounded response. Because some conversations are related to some knowledge. For example, this user wants to go to some restaurant, and your response should be, the information in your response should be related to this restaurant. Otherwise, the response seems very weird, although it's just a chatting. So based on this encoder-decoder framework, how to incorporate this knowledge? A very simple way is we just consider a lot of knowledge as a vector. For example, we can collect a lot of fact about this restaurant and use this fact to encode into the memory as a vector. And when we do the decoding side, they will automatically decide what kind of information should be related so that they can decode condition on this fact. So the whole model can be also trained in an end-to-end manner. But this information should be encoded and also fixed. They cannot dynamically change. So this can be work for like factual knowledge, may not work for the dynamically changed knowledge, just like weather. So using this idea, just like we want to have the conversational data, the conversational data provide us a shell of the conversation without the knowledge turn. And some knowledge resource will provide us the knowledge turn in order to generate the corresponding word. So we need to consider like both sides, how to generate the conversation and also how to fill in the knowledge word. It's also similar to task-oriented part. Like we have a designer semantic friend as the response and then generate the corresponding sentence. So they have some association, but not the same as each other. So using this idea, we can collect a lot of comment for example, for restaurant, and collect this information and store it into a lot of memory, and directly train this model to extract the corresponding information and to generate the suitable information as the response. For example, if the input is related to some airport, which is Los Angeles airport, and we want to have like the response, which is related to this airport, like nice airport terminal. So if this terminal is not nice, so it may not be good. So we want to collect some comment about the airport so that we can automatically generate knowledge-grounded information. And another example is this one. They want to go to some place, and this is the best street food in the world. So they will have like comment for this type of location and try this one. So they extract, automatically attend some knowledge in order to generate knowledge from the response in the end-to-end manner. But remember that you can only use this approach to the factual, like fixed knowledge. For the dynamically changed knowledge, this type of method may not work. So based on this paper, they show that the result can outperform like neural models baseline. And let's go back to this roadmap. There's another direction, which is the y-axis. In the y-axis, it is related to the complexity of the dialogue. Currently, our dialogue system focuses on knowledge base. Like we want to acquire some information, we want to book some ticket. But if we move forward, we want our model, our system can tell us, I've got code, what do I do? They can understand the common sense. If you have this problem, what is the best situation we need to provide? And further, if you feel sad, what is the best strategy? We want to consider the emotion, like to have an empathetic system. But this is very difficult because it's also difficult for human. So that's also very difficult for system as well. So how to move the more complex interaction? First one is we can consider like more modality and also consider the personalization. Let's see this example. If we listen to this utterance sent to Vivian, we may know that this person wants to do some communication. However, there are so many types of communication. For example, you can do email conversation. You can use message to do the communication. And the first one is, if we want to understand this user's intent, we need to consider the user's preference. For example, some people prefer message to email, and some people prefer email to message. We need to consider their own preference so that we can better understand their intent. And also, multimodality context. For example, this person, he took a picture, used camera, and then send to Vivian. Probably it's more likely to use message to do the communication. And if you use Excel first and then send to Vivian, for the same person, use the same sentence for different scenario. They may mean different intent. So it's more likely to have email communication after the Excel. So the behavior pattern in history is very important. So you need to incorporate like different modality. For example, like user's behavior or like visual information or others. So that you can toward like better understanding to common sense. How to extend to common sense? It's very difficult. So this is a very beginning attempt. It's trying to learn the high-level intent. For example, see this example. If we collect a lot of users' behavior with the mobile interaction, you will find this user will try to find a restaurant, use this app. Okay? After finding the restaurant, they check the location, use another app, which is another domain, location, map domain. And then they contact the person they want to meet for lunch. Okay, there are 3 different domains, 3 different apps corresponding to these 3 different domains. However, if you look at the user's intent, the high-level intent is this person wants to schedule lunch with Vivian. So that's why they need to check the restaurant and location and contact to Vivian. So if you have a smart Travis, you only need to say, I want to schedule lunch with Vivian. And the Travis need to decompose this high-level intention to multiple domains. They will automatically ask you the restaurant information first, and then tell you the distance, then ask you whether they need to send the information to Vivian by communication. So which is about common sense understanding. You need to have a common sense, schedule lunch with some person. It's related to the 3 domains. Like schedule lunch is related to find a restaurant, and then also related to like the person you need to meet. So you need to communicate with that person. So this very rich and difficult, complex interaction. But our ultimate goal is our Jarvis or our human agent can do this type of task. We're trying to understand your high-level intention and trying to decompose into several domains. And then you can interact based on the domain it decomposed. And the agent will automatically decide how to plan the whole dialogue to finish your high-level intent. That's why a lot of travel agents consider like hotel booking and also airline ticket booking. You only need to contact one person. They will automatically figure out all information for you, including multiple domains. But if you only build a system for each domain, you need to track like hotel and airline and back and forth. It's not convenient. So our ultimate goal is they can have the common sense understanding. So you don't need to talk about the detail. You can only talk about the high level intention. But it's very difficult, as you can see. And finally, how to consider the empathy in dialogue. This is a very basic approach. They're trying to embed an empathy module in a dialogue system. So you can imagine if we can recognize your emotion, probably we can provide you more emotion-aware response. So that's just build the emotion recognition based on the text and speech and visual. Because the text may include some maybe sad, this word, and speech, if we can tell whether you are not happy based on the tone. And the visual information is also very rich. We can tell based on your face. So after this information, we can recognize your speed, recognize your emotion, and trying to use this emotion information as part of dialogue act, a dialogue state, and then trying to learn how to generate the natural language based on the emotion and also semantics. So you will have the emotion-aware response in the dialogue system. It's a like simple trick to incorporate the emotion, but you can imagine emotion is very difficult to extract. Sometimes it's subjective and sometimes it's not universal. So some people have this face, may not mean unhappy. So it's also very difficult. And this is a very interesting area which is called cognitive behavior therapy, which is related to empathetic system. Because if you have a chatbot, it's more easy to approach the person. If you have a chatbot to chat with a certain user, it means you can track their mood and also mind their speaking pattern. If you detect there's a depression, and you can try to reduce the depression. Or sometimes if the depression is very serious, you can call a real expert to help you to interact with this user. And for example, you can provide some positive content, and the good thing is this bot is always be there. So if you under some depression, it's easy to approach the user compared to the real expert. And this chatbot may know you well because it always interacts with you. So they will know this type of pattern is regular pattern, and this pattern indicates this person is under the depression. So this is also another interesting area to explore. But as I said, emotion is very subjective and slightly difficult to measure. So how to incorporate in your system better is a difficult research direction. And finally, we want to summarize the challenge and make some conclusion. First, this human-machine interface currently is very popular, but you will see that there are several components must be integrated. So if your previous component may not perform well, and your follow-up component needs trying to recover or trying to do the confirmation, otherwise the error will propagate and the whole conversation will have very poor performance. And currently, a lot of techniques are based on deep learning. So the bad thing is we need a lot of annotation data. But the good thing is there are a lot of available framework, and you can directly borrow from like framework or the pre-trained model to your scenario. But you also need to consider your own application perspective so that they can work better for your application, because the dialog system is more related to the application side. So how do you do the domain adaptation? Because if you directly borrow some model from existing domain, they may not work better for your domain. So you need to do some adaptation. So how to do this adaptation efficiently, especially in the early stage? Because in the early stage, you do not have a lot of data. So your performance will be pretty poor. And if you have a built model, you want to extend to other domain, you also need to do the adaptation. How to reuse the previous rule or knowledge is very important. And then how to handle reasoning and personalization. This is a big challenge in terms of privacy, because we have a privacy issue, so we may not use a lot of personalization data, but we also want to provide you better interaction so that we can personalize the specific user. So this is a trade-off between personalization and privacy. And how to collect the data and also analyze by your own application is very important. Finally, because this is a very complex model, so if you want to have a better interaction for human side, it means each component needs to have very high accuracy. Otherwise, the error will propagate for multiple turns. Then the user will feel bad because they can only touch the final component's output. So if you have any error in the middle of the system, then the user will feel not good for your model's output. Finally, I want to finish this talk with another movie. This movie is called Her. Do you know this movie? Oh, okay. Actually, this movie is pretty interesting. Like, this person, they fall in love with his intelligence system. So it's like a cloud service. This intelligent agent. Because this agent understand this user a lot, and they will provide very personalized feedback and chatting with this user. And they find this is the only person they can understand him so well. So they just fall in love with this agent. So this is interesting because the ending of this movie is this person find that the cloud agent also interact with other person as well, because it's a cloud agent. So they just, his heart was broken. So this is the end of the movie. But based on this movie, I think we can try to think about what machine can achieve right now and also in the future. Do you want the machine to behave just like a real human, or the machine should behave just like an agent and try to help the human? It's a very difficult issue. It's related to ethics. So your afternoon talk will talk about ethics. So this is not a technical issue. It's about ethics issue. And finally, I want to play a very interesting like advertisement video, which is the Japanese product. And in this product, it's also the intelligent agent, but they have very cute avatar. And the functionality of this agent is not complex. It's very simple. You will see like weather checking or other like simple interaction. But let's play the video first.
朝ですよ。起きてください。ねえ、起きてってば。おはよう。
おはよう。
あ、今日雨が降るかもしれないから傘持って行って。急がないと遅刻しちゃうよ。
行ってきます。
行ってらっしゃい。気をつけてね。
19ページ、商品のラインナップについての。
おかえりなさい。
なんかさ、家で誰かが待ってるっていいもんだな。さっき思ったんだ。帰ってくるとき。おやすみ。
おやすみなさい。
So based on this video, we also have a lot of debate about whether the machine should behave just like a real human, or if in this way, like this person may not get any girlfriend, the real girlfriend. So, but sometimes if you think about, probably this person may not get a girlfriend at all. So having this intelligent agent may make his life better. I don't know. So there's a very big issues like debating between like the machine should behave like a real user or just like should behave just like a machine. Okay. So do you have any additional questions?
Inspired a bit by your last video, I was wondering, do you have anything we say about when you have conversations between multiple humans? Like the last video had it was human to bot. So is there work on bots with many humans? So.
Oh, I see. I think because they behave like an intelligent, like personal assistant, so it usually focuses more on the host itself. But if you want to build an agent which can handle like multi-party interaction, which is more difficult, the reason is, first of all, you need to understand there are several persons, and you need to maybe do the speaker identification, and some scenario is like in the smart speaker, because it's used for a family. So the family member, every person in this family can talk to this, for example, the Amazon Alexa. So this comes to a lot of issues. For example, previously there's a news about Amazon Echo. One girl in the family talked to the Alexa and said, I want like a doll and Barbie. And Alexa asked them, how many dolls you want? And the girl said, I want 100. So they just directly send the 100 to their family. So although you can return it free, but actually the better way is when we order this product, we need to recognize the current speaker is valid to make the order or not. So it comes a problem to do some speaker identification. That's why sometimes we need to have a camera to recognize whether, you are the current speaker, so you are allowed to make the purchase. But sometimes if we want to distinguish different person based on their voice, it's also another research direction to work on. And it's not very, currently it's not very mature. The reason is the audio for each person have a large variation, and sometimes if you are sick and the sound will sound different, then we need to consider this situation a lot. And I think it depends on the application. It works for a multiple person or like single person only. So you need to have a different interaction level for your intelligent agent.
I wanted to ask about the user authentication and verification of his identity. Can these systems incorporate a mechanism that's related to NLP in order to verify that whoever the user claims to be is actually that person, and start to reveal information or continue with a dialogue with that system? Or do we have to rely on mechanisms outside of the NLP field, like, I don't know, authentication with some kind of sensors or other machines system?
I see. I think it also depends on the application. For example, if you want to build a system for a call center, then no matter what kind of speaker you want to have like similar strategy to interact with, then you don't need to have a specific use speaker identification module in your system. But if you consider another application, maybe knowing the speaker profile is better. For example, if the call center is work for like insurance, so you want to have like more maybe rich interaction, so you need to know a lot of information about this speaker so that you can provide better interaction. Then you need to consider to build a speaker recognition first, and then incorporate the user profile in this system. So I think it all depends on the application usage. So it can be both ways.
So hi, I would like to ask about evaluation, and the question is, has there been a study that compares human evaluation and automated metrics, and if so, has there been found to be a correlation? And the third part of the question is, which evaluation metric is used more in this task?
Okay, I see. It's very difficult to answer. I think it's also related to the system goal. For example, the previous part of the lecture is about task-oriented. So the goal is, for example, finish the task, like purchase a ticket or book some table, or like maybe collect the answer for a specific question. So in this task-oriented system, like your goal is to have finish the goal in the user mind. So you need to consider how to measure the success rate. So for the first part of the system, usually we will treat the success rate maybe more important, and also the reward, because the reward consider the success rate and also the efficiency, because we want the interaction should be more efficient. But the later part is if you work on some maybe chit chat, you want your model to be able to generate like diverse output. So you can additionally measure the diversity in addition to like maybe blue score or roach score. So usually in the generation part, everyone will report the blue score, although the blue score has a lot of issues, but there's no better way to do the objective evaluation. So they will also report the blue score or like different like text automatic metrics, and also include more evaluation metric which is related to your application. For example, if you want to check whether this output contain more diverse response or not, then you can measure the diversity of the output and to have an additional metric so that you can show to the readers then your model have not only have a better sentence generation, but also you focus on more diversity in the response. So you can design your own evaluation metrics. So I think there's no like universal metric for every task. It always depends on your application site, because this is all related to application usage.
I have a question regarding the multi-domain dialogue problem. And I'd say that I'm not sure how one goes to implement a chatbot, let's say, that handles multiple domains, like for example, the pizza place, like the restaurant problem, but at the same time it can be a general chat bot, a chit chat bot, and also it can be a weather bot, it can be like, and maybe all this can be towards the direction of a general AI, which is of course not something we can do today, but let's suppose we're trying to achieve a general intelligent bot. And I'm not sure how one can go to implement the switching, let's say, mechanism between domains. So for example, if you are if you are chatting with a bot about a specific problem, about something, and in the middle of the conversation you switch the context and you say, oh, and what about the flights tomorrow, or what about the weather tomorrow? Oh, and by the way, I'd like to go to that restaurant. So you might have a stack of context switches. You might have trouble going back to the previous domain because it might not have sense to return at the point you were before, because the user might not remember the exact point of the conversation. So the user might need refreshing. Let's say if you're in the middle of ordering a pizza and you talk about the weather and then you go back to the pizza, you can't just keep adding ingredients to the pizza. You started adding ingredients 10 minutes ago. So what I want to say with this lengthy question is that has there been an attempt to create a hierarchical design in chatbots, like maybe an orchestrator that only takes care of high-level stuff like domain switching, and then each I don't know, models for every domain? Is there? Do you have any also examples in the market or in or any frameworks?
Okay, sure.
Yeah.
Yeah, this is very important, especially in terms of the application side. And for the current product in the market, they will have like two different variety, just like as you said in a hierarchical way. For example, the shell eyes, because the main idea is the engaging like empathetic chit chat bot. So the framework is focused on the chatting. Then they will have additional classifier to detect whether this current sentence includes some skill, which related to, for example, some domain. For example, if you do the chatting and in the middle you want to order some food, and if detect you have like task-oriented intent, and they will enter in the task, for example, food ordering bot, and trying to help you to finish the food. And you return to the shall I say, which is also the chatting mode. Then they will collaborate with different domain coherently. But if for another bot, if this bot focuses on like more task-oriented, for example, they trying to a travel agent, they were trying to book the ticket for airline and also like the hotel, then the whole framework associated with the task-oriented. But they also want to incorporate some chatting function in the middle. So it used very similar way, just like during the task interaction, they will also detect whether the current utterance belong to like some chatting, like greeting. Then they will incorporate the chatting mode like as the response to the user, but they will still track the current dialogue state, which is related to the task, and the user can go back to the task after doing some chatting. So just like the main goal of the system is chit-chat or the task-oriented, so a lot of products doing in this way. But I think ultimate goal is we don't need to have like this design. Probably we can try to allow our model to learn how to switch between these two modes. So there's some work also from Microsoft Research. They're trying to use like hierarchical reinforcement learning. Like because for each domain, they have a reinforcement learning agent to do a dialogue, right? But to switch the domain, these things is also very difficult because you can book the flight and the hotel and maybe some taxi in the same system. But how to switch between these three different complex domains? They need to have like additional reinforcement learning agent to decide which domain you need to fill in. Then after decide this domain and domain-specific reinforcement learning agent will try to generate the interaction. So they will collaborate with two levels of the reinforcement learning agent. But I think it's still it's very difficult because you also need to have like a user which can speak with you for the multi-domain scenario.
Great. Just say that I think we should break for lunch now. Let's thank Vivian again.
Thank you.